So this section is about solving equations that imply formulas. I'll show you what I mean by this. And let's start with a little application or a problem that's that you probably know, which is the problem of finding the area of a cylinder. Okay, so I want to find the surface area. So I want to find the area here. So below also, add this up, and also the area that's on the side of the cylinder. So I need to add three things, right? I need to add the area of the top part. So we'll assume that this cylinder has a radius of r. So we have the area of two discs to add. So the top part is the area of a disc with radius r. So that's pi r squared. So I've got pi r squared, but I've got two of those, right? So the bottom part is also pi r squared. So 2 times this. Let me rewrite it nicely. And I also have the side of the cylinder to take into account, and the area of the side. So imagine that imagine that I have a pair of scissors, and I'm going to cut this and unfold my cylinder. Actually, maybe this is a good way to see what my area is going to look like. I would end up with something that looked like this after cutting it open. Okay, so I've got my pi r squared here, pi r squared there, and then I need this area here. And what is it? Well, the height of my cylinder is h, so all I need is this part. And this is just once I form the cylinder, it's gonna this side here that I have here, right? It's going to be able to wrap around my circle, so it has the same length as the circumference of the circle, which is 2 pi r. So the area here inside is, well, so the area just of that part, that's 2 pi r times h, right? So it's the area of a rectangle with height h and width 2 pi r. So what I need here is 2 pi r h. And that's great, right? So it's going to give me the area if I know r, if I know h. But what if instead, and the a here is the surface area. R is the radius, h is the height. And that's great, right? If I know radius and height, I can find area. But it should also be true that if I know the, let's say the area, I should be in the radius, I should be able to find the height. So that's kind of my question here. What is h if we are given r and a? So what I'd like to have is kind of a formula for a, but for h instead. H is equal to some expression involving r and h. And how do I do this? Well, all I have to do is play with this equation here and solve for h. So I'm going to solve the previous equation for h. So I'm going to consider that everything else but h is known, so it's some sort of constant, okay? So how do I do this? Well, just to give you an idea, let's start with numbers. I know that students, they like to work with numbers first, or at least they picture things better with numbers. Let's say a is 4, r is 5. See, it would be 4 here. I would have 2 pi 5 squares, which is 25, plus 2 pi times 5 times h. Okay? So it would be 4 is equal to 50 pi plus 10 pi h. And how would we solve for h here? Well, we would send this on this side. And After that, we would divide by this to get rid of that coefficient. So we would have 4 minus 50 pi over 10 pi is equal to h. Okay, but now what I'd like to get is a formula that works for any r, any a. Okay, so I'm going to repeat those steps with some arbitrary a and r. So you start with your equation. And what did we do? Well, first thing we did is we sent the 50 pi on the other side. Well, that's this part, right? This part has no h in it, and we're going to send it on the other side. And then we have to, what did we do? We got rid of the 10 pi, which was the coefficient of h. Well, what's the coefficient of h now? It's 2 pi r. So I'm going to have to divide by this. All of it, right? And that gives me how h is obtained when I have a and r. This is a formula for getting h. So that's what we call solving this equation for h. So in this section, we're going to work with equations that have many variables, and we're going to solve for one of the variables. Okay, so for example, here's another one. Solve for variable a. A times x minus y plus 2 is equal to b. So I just want to have this solved for. Okay, so what do? I get rid of the 2. And even though I've got x and y, those are not my variables here because I'm solving only for that one. So they're considered, I treat them as constants if you want. Okay, a is my variable. Here's the thing I want to solve for. How do I get rid of x minus y? Well, I divide by x minus y on both sides, right? So this is what I do here, right? Divide by x minus y, everything, right? On both sides. And if you do that, you get b minus 2 over x minus y. Okay, you don't want to expand, by the way, right? If you expand here, you're going to be stuck because you're going to have a in both places here. And if you start sending this around, now it's even worse. You're going to have a on both sides now of the equality sign, and you don't want that. So that's why really you get rid of x minus y by dividing by all of it on both sides, and you've solved for a. Note that there are different ways to write down also this answer. You see, if I've got a fraction, if I multiply by minus 1 at the top and at the bottom, I'm not changing the fraction, right? If I've got 3/4 and I multiply by minus 1 on both sides, I get minus 3 over minus 4. That's still 3/4. If I multiply by minus 1 again, at the top and at the bottom, I get 3/4, okay, and so on. So I'm multiplying by minus 1. I'm not changing anything. But what it does, though, is that you see it's going to change the way the subtraction is done. So here, if I multiply by minus 1, I get minus b plus 2 over minus x plus y. And if I can rewrite everything like this. So you see, that's another way of writing down my formula for a. And you'll notice that at the top and at the bottom here, the order of the subtraction is the opposite of what I had initially. So I can always change the order of the multiplication of the subtraction if I want to. Okay, but I have to do this at the top and at the bottom. It's just I'm just saying this because sometimes you'll look at the book and that's going to be your answer, and this is maybe what you calculated. Just know that those two are identical. Okay, I'm going to do another one. We're going to solve once again for a, and I'd like to solve, this one has fractions. A over 2b plus c over 3b is equal to e. So notice that this is an equation with fractions, and I've got different denominators. I recommend, instead of sending this on this side first, to clear the fractions. So how do you do that? You want to put everything over a common denominator, and we got 2b, 3b, okay? They're both multiples of b, so you look at the multiples of 3b. You've got 3b, 6b, 9b. Can you fit 2b in one of them? Yes, I can fit 2b and 6b. Okay, so that's the common denominator that I want to use. So I'm going to use 6b. Okay, and even on the other side, I'm going to put everything over 6b so that I can clear the fractions. So E is going to be 6EB over 6b. This I need to multiply by 2, right? By the way, if you're not convinced, right, to get over 6b, I need to multiply by 6b and 6b at the top and at the bottom. That's how I got 6EB. Here I get 2c, and here I multiply by 3 at the top and at the bottom. I get 3a. And now I'm going to be left with only that because I'm going to multiply on both sides, right? I multiply by 6b everywhere. So multiply by 6b, all of that, right? So if I multiply by 6b, because this is the same as 3a plus 2c over 6b, right? So by multiplying by 6b, this is going to go away. So I'm just left with this now. 3a plus 2c equals 6eb. I don't have any fractions. I'm going to send the 2c on the other side. And I'm going to divide by 3. I can't simplify the 3 with 2 and 6. Okay, so they share nothing in common. So this is how it would I would leave it. But of course, you could match up. Another possibility is just to say, oh, I'd like to match up the 6EB with the 3. Now, there's nothing that I can do with the 2 and the 3, but with the 6 and the 3, I can, right? This is 2EB minus 2C over 3. So that's another possibility for writing down your solution. 2EB minus 2C over 3. It's just a different way of presenting it. I'm going to go through a few more examples here. So I want to solve for b. A is equal to a over 2 minus b. So I want to solve for that now. Okay, how do I do this? Well, first of all, b is in the denominator. I'd like it to be in the numerator. I'd like to have b equal to something, so it should show up in the numerator. So what I'm going to do is multiply by 2 minus b. Right, in order to cancel this with this, right? So I've got a times 2 minus b, careful, you have to put your brackets because a multiplies everything, is equal to a. Now I am going to expand this because ultimately I just want to have the b on, actually maybe I don't need to expand. You know what, we can get rid of the little a there, like that, divide by a, and then I'm going to get rid of the 2, and what I have is minus b. So minus b I multiply by minus 1 on both sides. So in other words, it's going to change the order of the subtraction here. This is kind of what I mentioned before, right? If you multiply by minus 1, you get minus a over a plus 2. So actually it looks nicer if you write it as 2 minus a over a. If you want to have this over a common denominator, it's also possible. So, you know, there are different ways to present your solution. Okay, and we're going to solve another one. This is our final example. Solve for b again. And this time it's 2a plus 1 over b is equal to a over 2 minus b. And how can we do this? I'm going to go step by step here. Maybe I'll show an identity here that's going to be pretty useful. Let's say we've got a over b is equal to c over d. Notice that I can get rid of, let's say I don't want to have fractions. I can get rid of the b by multiplying by b on both sides. And I can get rid of the d by multiplying by d on both sides. Okay. Now that's on the right hand side. I've got b over b. That's 1. So they cancel out. So I'm just left with ad on that side. And on the other side, I've got d over d, which is 1. So I'm just left with CB. So let's summarize what we have here. If I have A over B is equal to C over D, that's the same thing as AD is equal to CB. So in other words, we're kind of doing what's called a cross product. We're multiplying A with D and C with B, okay, and those are equal. So I'm going to apply this principle here because I've got two fractions here. So what I have here is kind of like an A over B is equal to a C over D, even though my A is the C. But I'm going to apply the principle I just explained here to get rid of my fractions. I'm going to cross multiply like this, and so we got 2A plus 1 times 2B. 2 minus b is going to be a times b. So that's by cross multiplying. I got rid of the fractions. And I want to solve for b, right? So look, I'm kind of in a bad situation here in the sense that I've got b on both sides. So I'd like to regroup them, but to regroup, I'm going to have to expand the left-hand side to be able to just take the expressions that involve b. So if I multiply out these polynomials, I get 4a minus 2ab plus 2 minus b is equal to ab. And now look, I'm going to be sending all those terms on the other side so that now all my b's are on the same side. Of course, the sign is changing as you send them. After that, I have b that's common to all of them, which means I can factor that b. And what's inside my factor, okay, that's in my factor here, doesn't contain b anymore. So I'm going to divide by it, so I'm going to send it down by dividing by it. And finally, I've got my answer. So this one's it's more difficult than the others, but it shows you the cross product. That's kind of really cool, right? Which you can apply in other situations. If you've got this, for instance, you can cross multiply and get immediately an equation without fractions, right? And then you can factor to get your solutions. So cross multiplying is really cool. So you see I've got root of 18 minus root of 18 here very quickly by doing cross multiplying. All right, so this is a principle I wanted to show you that's really useful in practice.